Hello everyone, welcome to Energy Conversion 2 class. We are going with chapter 7, that is 3-phase transformer. Today we will discuss about 3-phase transformer connection. There are various methods available for transforming 3-phase voltage to higher or lower 3-phase voltage, that is for handling a considerable amount of power, and for this purpose only we are going for using 3-phase transformers. Usually star connection is used for high voltage transformation and delta connection is used for high current transformation. And also the most common type connections are like number 1 star star connection, number 2 delta delta connection, third one is star delta connection, and the fourth one is delta star connection. Now you can see the first connection type, that is star star connection. It is also otherwise known as Y-Y connection. You can see here with these phase angles the center point of Y or star must tie either all negative or all positive windings ends together. As we know, either the starting end or the finishing end of this winding are to be connected to form a star connection. So here we can see all the negative ends are connected at a single point, that is the center of Y, and here all the positive connections are outwards. So this is the connection for star. We can see the phase angles. This is plus 120 degree, this is 0 degree, this is plus 240 degree. Again, here is the delta connection. With these phase angles, the winding polarity must stack together in a complete manner, that is positive to negative. Here we can see from positive to negative, and this is delta connected. We can also see the phase angles here, likely as the star connection. Again, star star or Y-Y connection again. This we can see with zero angular displacement. This figure 2 indicates the zero angular displacement. Here we can see the three different windings. This end is A, B, C. This is capital A, B, C, and this is the neutral point. And here we can see these are the two Y-Y, that is star star connection with zero angular displacement. There is no angular displacement. Now this connection is most economical, this star star connection, for small high voltage transformer, because the number of turns per phase and the amount of insulation required is minimum. We can say as per voltage is only 1 by root 3 of the line voltage. We can say the phase voltage is 1 by root 3 times of the line voltage. So here the number of turns per phase and also the amount of insulation required is minimum. So this is very economical one. We can also say in figure 2 a bank of 3-phase transformer we have already seen. Those are connected in star on both the primary and secondary sides are shown. The ratio of line voltage on the primary and secondary sides is the same as the transformation ratio of each transformer. Be very clear. However, there is a phase shift of 30 degree between the phase voltage and the line voltage on the primary and secondary sides. Of course, the line voltage on both sides as well as primary voltage are respectively in phase with each other in star-star connection. So, this connection works satisfactorily only if the load is balanced one. With the unbalanced load to the neutral point shifts there by making a 3 line to neutral, that is phase voltage unequal. So this star-star connection is suitable only if the load is balanced. Otherwise, we will go for using a neutral line. The effect of unbalanced load can be illustrated by placing a single load between phase or a coil. How? And the neutral on the secondary side. The power in the load has to be supplied by primary phase or coil A. This primary coil A cannot supply the required power because it is in series with primaries B and C, whose secondaries are open. So this will not be able to supply the required power to the unbalanced load. Under this condition, the primary coils B and C acts as very high impedance, so that primary coil A can obtain but very little current through them from the line. Hence, secondary coil A cannot supply appreciable power. In fact, a very low resistance approaching a short circuit may be connected between the points A and the neutral, and only a very small amount of current will flow. This, as said above, is due to the reduction of voltage E because of neutral shift. In other words, under short circuit condition, the neutral is pulled too much towards the coil A. This reduces EAN but increases EBN and ECN. However, we know line voltage EAB, EBC, ECA are unaffected. EAB is the line voltage from A to B phase. EBC is the line voltage from B to C phase. ECA is the line voltage from C to A phase. On the primary side, EAN will be practically reduced to 0, whereas EBN and ECN will rise to nearly full primary line voltage. Again, this difficulty of shifting neutral can be obviated by connecting the primary neutral, as we have shown it indicted in the figure itself, back to the generator, so that primary coil A can take its required power from between its line and the neutral. It should be noted that if a single phase load is connected between the lines A and B, there will be a similar but less pronounced neutral sheet, which results in an overvoltage or one or more transformers. Another advantage of stabilizing the primary neutral by connecting it to neutral of the generator is that it eliminates distortion in the secondary phase voltage. That is, this neutral can reduce the distortion, the disturbances in the secondary phase voltages. This is explained as follows. See, for delivering a sine wave of voltage, it is necessary to have a sine wave of flux in the core, obviously. But on account of characteristic of iron, a sine wave flux requires a third harmonic component in the exciting current. So what happens here? As the frequency of this component is thrice the frequency of 3 circuit, at any given instant of time, it tends to flow either towards or away from the neutral point in all the 3 transformers. And if the primary neutral is isolated, the triple frequency current cannot flow. Hence, The flux in the core cannot be a sine wave, and so the voltages are distorted. So here we can conclude that there is a biggest advantage of stabilizing the primary neutral. Okay, after stabilizing, after connecting it to neutral, what will happen? It will eliminate the disturbance, the distortion in the secondary phase voltages. But if the primary neutral is earthed, that is joined to the generator neutral, then this provides a path for the triple frequency currents and EMFs, and the difficulty is now overcome, is solved. Another way of avoiding this trouble of oscillating neutral is to provide each of the transformers with a third and tertiary winding of relatively low kVA rating. This tertiary winding connected in delta and provides a circuit in which the frequency component of the magnetizing current can flow, or we can say with an isolated neutral it could not flow. In this case, a sine wave of voltage applied to the primary will result in a sine wave of phase in the secondary. And also, as we have discussed above, the advantage of this connection is that insulation is stressed only to the extent of line to neutral voltage, that is near about 58% of the line voltage. Thank you. In the next video, we will discuss about the delta-delta connection.